Today we are going to talk about the presentation of CUDA programming and the CUDA architecture. Okay. So I'm hoping that everyone can see the presentation right now, and we can begin. All right.
Looks good. We can see it on our end.
Yep. Okay. So hello, everyone. Welcome to the presentation on Introduction to CUDA Architecture and Programming. Today, we're going to see the difference between sequential and conventional programming using CPU, and also the difference that the architecture of CUDA and the programming language makes when you want to program parallel programs. So my name is Omid Hajasani. I'm the ML and client analyst at ISAIC. So as the introduction, let's take into account what was the design goals when they wanted to build out the CPU and the main CPU of the computer, and also upgrade and through different evolutions of the CPU. What were the main design goals? So the first one was that they wanted to have a fast execution of sequential code. And to achieve that, they had to incorporate larger cache and out of order execution of code. They wanted to achieve multitasking rather than parallelism, and multi-cores that are strong and big cores rather than a handful of cores, rather than thousands of hundreds of cores that are present in CUDA. The cores in CPUs in laptops are essentially up to 8 cores, and in server grade CPUs, you can go up to 60 or 100 cores at a time in a CPU package. So how can the faster execution of sequential code be feasible? It was made feasible through sophisticated control logic. As I mentioned, they achieved out of order execution of code, meaning that parts of code that were stalling would be stopped, and the program would begin and finish other tasks within the same program that did not require waiting for I/O, for example. So out of order execution of code. And also, this would mean that they had requirements of large cache sizes to meet the fast sequential and out of order execution of code in order to reduce the instruction and data latency and the data availability for CPUs. So the sophisticated control logic meant that it would be advanced and also costly, which is nowadays one of the main pain points of the architecture used by Intel and AMD, rather than the architecture RISC or the architecture that is used by Apple to build the M1 Max, and which achieve faster computation and better speeds and at lower TDP. So it requires advanced costly control units, and also larger caches require more on-chip area dedicated to caches. But what was the initial goal and the goal when they wanted to upgrade and build more advanced versions of GPUs? It was the high computation throughput goal, and it was fueled by the driving force behind GPUs. That was the main industry involving the gaming industry. Due to the requirements of the gaming industry, GPUs had to be able to perform a massive number of floating point calculations simultaneously and at once, which meant that the architecture should have been different from the CPU architecture. And that makes GPUs, given the performance overview, apart from the CPU, and CPUs, as I mentioned, are good for fast sequential execution and general purpose program execution. And also GPUs are, on the other hand, well suited for high computation throughput and are mostly designed to do simple instructions, but at a large scale, rather than general purpose computation. But how can we use both of these architectures to our benefit? We can use a heterogeneous approach. CUDA programming architecture is essentially a way to utilize this heterogeneous approach and utilize both CPU and the GPU to meet the program execution of a fast parallel execution and also fast sequential execution in programs that are in need of such execution. So from the programmer's view, this heterogeneous approach divides up the code into distinct sections, the sequential and the parallel sections. Intuitively, the sequential sections would go to the CPU to be processed, and the parallel sections would be done and executed by the GPU. Here we can see an example of how a single program and a single code can be divided between the CPU and the GPU. They can be interlaced, and you can see, and interleaved. As you can see, the sequential parts and the parallel parts can come between each other, and the sequential parts go to the CPU to execute, and the parallel parts go to the GPU. And this is all handled and managed by the host, which is designated as the CPU. And in this architecture that CUDA uses, the GPU is referred to as the device, meaning that a GPU is only seen as a compute engine to handle parallel tasks, and the main operations and the main code resides on the CPU and the CPU memory and the system's memory. Okay, so before CUDA and before the introduction of CUDA by NVIDIA, I must say CUDA means the Compute Unified Device Architecture. And before the introduction of CUDA in 2006, the main approach that was adopted to program GPUs was the general purpose computing on GPUs, or GPGPU, was programming using OpenGL, which is a graphics library, and it had some downsides. Downsides was that they had limited instruction sets due to their nature, and programmers had to mostly represent the data as picture elements and pass them, and textures, and the operations would have been shaders, which are graphical operations, rather than operations that you would use in a normal C programming and a normal C programming code. But after that, NVIDIA came up with CUDA, or the Compute Unified Device Architecture. CUDA is both the architecture that NVIDIA uses to build out its GPUs, and also the programming API that can be used using C, C++, and Fortran and other languages to interact and use the architecture of the GPU in your programs. As I mentioned, it can be used and triggered through minimal extensions and directives used in the C, C++ programming language, and is essentially suitable through in-program variables defined by CUDA. You can use the GPU architecture and map threads to your program, as we are going to see, and call the memory APIs. So from the programmer's view, after using CUDA, we are going to support both CPU and GPU execution through our CUDA application. So the developer can use a single GPU or multiple GPUs, and the memory of can allocate and use the memory of the GPUs, and also can use and allocate data into the memory of the CPU and execute code on both of them. As we said, the system is divided into the host, which is the CPU, and one or more devices, which are referred to as the GPUs or the graphical processing units in the system. Till now, we were talking about dividing the program between sequential and parallel sections. It might be counterintuitive because the CPUs are essentially capable of doing multi-threading and SIMD and all sorts of parallel programming paradigms. But we refer to the massively data parallel problem as the parallel problem that GPUs can handle. So what is essentially the data parallelism that GPUs are good and are a fit to handle? So in the data parallelism problem, we have large amounts of data and data intensive operations that are essentially simple operations, but are going to be happening on thousands or millions of data points in parallel. And each data point can be processed independently from the other one, or the dependence can be handled in a parallel way and can be divided into parallel sections. So the task that we want to do should be parallel in nature, given the data that we have. So let's see. A simple example from nature is the raindrop simulation. Say that we have a task, so we are programming a code which is going to simulate raindrops. So don't think about the graphical side of it, but only think of it as simulating the gravitational forces being exerted on the raindrops themselves. So we have thousands of independent raindrops because think of it, whether we have one raindrop or billions of raindrops, they are going to fall independently from each other, and gravity is going to be affecting each of them independently from each other in this simulation that we have. In the nature, in real world, there are different forces. You have wind gusts and you have different things, but let's only take into account the gravity. And they're falling at the same time, so they're falling simultaneously. As you can see here, we have a data intensive task, meaning that we have lots of data, but the operation is simple, meaning that we are only going to calculate a simple gravity equation and the role it has on the fall of the raindrop, but we have many data points to simulate. So this is a textbook example of a data parallel and data intensive program that we have to run. So GPUs are good for these kinds of and these sorts of problems. Now let's look at the examples that are more mathematical. So as we mentioned, we have vast number of operations that are better to be simple and that are going to be running concurrently on the same data. So for example, from math, if we have element-wise array addition, if you have two vectors that we want to add them to, element by element together, it can be seen as a data-intensive problem, and you can essentially do each addition in parallel and independently from each other, or you can do matrix dot product. In the case of matrix dot product, we have some kind of dependency between the data elements, because once you do the product, you have to add the elements together in order to get the so it's a MAC, it's a multiplication and accumulation problem, but you can achieve the parallelism and you can handle the parallelism on the GPU using reductions. So reductions are a bit advanced for this presentation, and we are not going to cover that. But for those that are curious about it, after this talk, you can look into how to do matrix dot product. We are only going to cover element-wise array addition. Okay, so the the program that we have and the data intensive parallel program and problem that we are going to solve that by the SIMD paradigm or the SIMD paradigm, which is single instruction, multiple data. There are different paradigms and different names. You can name it single program, multiple data, or different other, or single instruction, multiple threads in the case of GPUs. But the idea is that either we have a single program or we have single instructions. Each execution unit within our GPU, which we are going to next, what would be the execution unit, which we are going to see what would be the execution unit, has a single instruction and wants to do that for multiple data in parallel. So for example, we have a program, we have an instruction, our execution unit takes that single instruction or single program in the case of SPMD, and then loads into itself different data 1, data 0, and data 2, and then outputs the results of the operation and instruction in parallel to each other. So that's the paradigm that we are going to use when we want to solve the data intensive problems that we are going to solve. So I talked about the architecture and the design goals of the CPU and the GPU. So this is a GPU from NVIDIA. We have GPUs from AMD. In AMD, we have HEAP, which is the heterogeneous so the name is not on top of my head, but the HIP is the CUDA alternative when you go to AMD. So the architecture is the same in the case of the GPU designed by NVIDIA and AMD. So given the CPU, as you mentioned, you would have a strong ALU, or for example, CPU cores. You will have a control unit that is big and large to handle out of order execution and to speed up the execution of a sequential program, and large cache, as we mentioned. But in the case of the GPU program, the GPU that we have from NVIDIA, you can see that we have simple small ALUs, but in large scale and large numbers. So rather than having only 4 strong cores, if we can map ALUs to cores, we will have thousands or hundreds of simple, lower power ALUs and cores, and we would have single control units controlling multiple batches of those cores altogether. And this is one of the limitations of GPU. And this limitation is that while we are going to run our program, as you're going to see, we have cases that we cannot have divergence in the instruction that we are going to run on the cores, because a number of cores, 16 cores or 32 cores, are controlled by a single control unit and a single cache. So if the program that they are running diverges, for example, if there is a true or false statement and an if condition evaluation happening, and the threads and the programs that they take diverge, the control unit should stall half of the cores and then run half of the other cores. And it would be incurring issues within the speed up that we can get from the GPU. But these are fairly advanced topics from the performance arcing topics. So these are not also covered in this presentation, but I encourage you to, if you like programming with CUDA, to study more on this topic as well. So now let's look at the CUDA program structure. As we mentioned, this might be repetitive, but as we mentioned, those sections that don't have any data parallelism, those sections that only include initiation of data, moving data between the CPU memory and the GPU memory, should be residing on the CPU side. So host should handle those, because GPUs are not designed to do those things. And those sections that are data intensive should be happening on the GPU. And we can essentially mark and label these different sections through directives that are provided by the CUDA programming API. So let's now look at the execution path of a single GPU kernel. So as I mentioned, those data-intensive parts that are going to be running on the GPU are labeled as kernels. So those functions that we are going to invoke on our GPU to handle, for example, if we are going to simulate a raindrop simulation, that raindrop simulation is going to be housed within and is going to be abstracted through a function call. And that function call is simply referred to as a kernel. So it's just a name for the function call that is going to be invoked on the GPU. So these strings are threads. So it's a fitting representation for a thread because it can be shown as a string. Our serial code can have multiple threads, for example, 10, 20, 50, but we are just going to show you a single thread. So for the serial code that's running on the CPU, we have a single thread handling that GPU serial code. And now that data-intensive kernel and parallel kernel that we are going to run on the GPU spawns multiple threads within a grid architecture. Next, we are going to see what is a grid, what's our blocks, and how these threads are organized and organized within the organization of grids, blocks, and threads. But you can see there are, and after the single thread goes into the GPU, we spawn hundreds or thousands of threads to handle the data-intensive part. And then we get back to the CPU, to that single thread. You can call it the master thread. In OpenMP, they call it master, and they do forking. And this can be similar to the fork and join from the OpenMP, but it's not the same. It can be viewed as a similar way. So as I mentioned, CPU is referred to host, and you can kind of sense through that terminology that is chosen by CUDA. The host has more control over the device. So CPU and that single thread that you saw controls kernel invocation, kernel launch, data copy back and forth to the GPU memory on the GPU. So all of those parts are handled by the CPU. The GPU calls and the kernel calls, in the previous slide, the illustration that was given, we saw that the CPU waits for the GPU to run its program, but this is not the case. It can be synchronous or asynchronous with the CPU. In the synchronous fashion, you can see that the execution is passed back and forth between the CPU and the GPU. And this is the program execution over time. You can see some parts are executed in the CPU, and then we go to the GPU, and some time is spent between this transition. You see that this is not a straight line, meaning that from going from the CPU to the GPU takes time, and the kernel invocation, data copying takes time, and this can be seen as the data copy time, the time that it takes for the CPU to pass to the GPU. So let's get into the description of what a kernel is. As I mentioned, kernels are those part of the program that we are going to run on the GPU. So we are going to abstract away the function that we are going to run on the GPU as a function, as a simple function that we refer to as a kernel. In order to, for example, if you're familiar with C programming, just don't look at this global directive. In a C program, you essentially define a function as the return type. Here we don't return anything. In the GPU function calls, the return should be handled by the reference arguments, and all the arguments and the data copy from, and the data return shouldn't be handled by any return type or expression in the code. We use this global directive as a way to tell our compiler that, hey, this is a kernel code, this is a GPU code, this is a function that's going to be executed on the GPU. And it's that simple. You don't have to do anything. So as I mentioned, the global identifier, and you see these are 2 underscores. So each of these sections are 2 underscores in a sequence. And it should be void as a return type, and the returns are handled by references. So it's that simple. Later on, we are going to see how we can essentially write a kernel code. As an example, we are going to use the vector summation. So, but we define the kernel code in our C code by using that global directive. So next, we are going to call and invoke it. So there is a term that's used, is kernel invocation. Rather than calling it a function call, they call it a kernel invocation, but it's the same. You just call the function. There is only one difference. So the similarity with conventional C functions is that you have to call the function through its name. So it's the kernel's name, the function's name. You have to pass it different arguments that it requires, so input arguments. However, the difference is that within these chevrons, within these 3 chevrons that we have here, you have to pass it the grid and the block size and the threads, organization of the threads that the GPU is going to spawn in order to handle the function. So as we saw, GPU is going to spawn different threads to handle the data intensive task. So here we are simply giving the GPU instructions to run that kernel with these blocks and these number of threads. We are going to see that later, so don't worry about it. We are going to discuss that in depth. So these are simple parameters, and these parameters, as I mentioned, control the size of and the number of threads that are going to be spawned in the GPU in order to execute the function and the kernel. So as we mentioned, each kernel spawns a set of configurable, but this term shouldn't be misused. By configurable, we mean at the compile time. At the runtime, the size of the GPU threads is fixed and you cannot change that. So it can be a dynamic parameter, but once the program is compiled, it should be fixed. So, and the total number of threads in a kernel are referred to as a grid. So if the kernel spawns k threads, a grid size of k threads, then there are k execution units or execution threads that are going to be running the same task and the same program and are going to be spawned in the GPU. So don't let the name and the terminology scare you. So it's just simple organization. As you saw, we have different kinds of programs and different kind of data intensive, for example, data intensive tasks that we are going to parallelize through our GPU. In order to do that, in order for our GPU to be able to map each data to the execution units, we are simply going to spawn threads which are organized within blocks and which is housed within a grid. The block, the threads, and the grid can be a 3-dimensional organization of things, of threads, meaning. So here we see a 2-dimensional grid with 1-dimensional blocks. So simply, the threads are within each block are 1 dimension, meaning that we have only threads numbered by single dimension, 0, 1, 2, and 3. And also the blocks are organized into a 2-dimensional fashion within the grid. So block 0, 0 and block 1, 1, this is the row and the column that the blocks are organized in the grid. So this shouldn't be a real head scratcher. So most of the time, the program architecture and the data architecture that we have mandates different organization and different ways. So for example, in this case, we had a task that we wanted to use one-dimensional threads with one-dimensional blocks and two-dimensional grid. And this is dictated by the data that we have, meaning that if you're going to do matrix multiplication, it makes sense to maybe organize our data into blocks and into blocks of two-dimensional threads. If you're going to do vector summation, we want our things to be one-dimensional because our vectors are essentially one-dimensional. It makes sense to map our threads to be one-dimensional as well. It can be tricky to understand because it is a bit abstract, the way that we want to manage and handle and organize our threads within our grid. But I think it's enough for the presentation today to talk about it. We are going to see examples, but don't let that spook you in some sense. So essentially, what are blocks? So each block is comprised of a number of threads. So when you run a block, when you have a GPU, the GPU that we have, for example, in the CUDA terminology and in the CUDA architecture, we have a streaming multiprocessor. Streaming multiprocessors each have a number of CUDA cores, okay? Each streaming multiprocessor takes into a couple of blocks that is going to run given different instructions within those blocks and is going to dispatch each block within its CUDA cores. So as you saw, we have a controller for a number of cores in the case of the GPU. We had multiple cores, we had single controllers for all of those cores. So the controller is going to dispatch a number of, is going to load and then dispatch a number of blocks. So within the block, we have different memory units. And the amount of memory that each block is going to get from the local memory, from the register bank, and from the shared memory is going to be limited. But as we are not going to talk about shared memory in this presentation today, I'm not going to talk about that. But it's important for you to know, as we are just introducing the blocks, each block, rather than an abstract compartmentalization of different threads and categorization and organization of threads, is going to have some implications in the hardware, meaning each block and the threads within each block can communicate together to each other through the shared memory, are going to be running together. If one stalls, maybe the dispatcher and the controller is going to preempt the block from execution. The data access can be cached within a block. So it matters if you're going to look into the details and the hardware details, but the most important part is that the threads within a block are going to be dispatched to be run in simultaneous warps. In AMD, they call it wavefronts, and in CUDA and NVIDIA, they call that warp. And it's important that 32 threads are going to be from the same block are going to be executed simultaneously within each SM and streaming multiprocessor. So as we mentioned, threads are going to be executed in batches of 32 threads from a single block, and there is no deterministic order in which blocks are going to execute. So one thing that you have to keep in mind while you're going to use GPU programming CUDA is that the order at which each thread is going to execute cannot be foreseen. Like, for example, if you have thousands of threads, it might be that thread 1,000 is going to run and execute sooner than thread 0. And there is no sequential correlation between the naming of the threads and their execution manner and execution order. So it's important to know that. So now we are going to see how we can map threads to data. So each thread within the global grid has identifiers to essentially identify the position that it has within the grid, to get the global address that it has within the grid. And we use that in order to map each thread to the data that it has. So as I mentioned, threads are execution units, abstract execution units that are going to run on the GPU. So each thread should have access to its own data to process. And we are going to map each thread to each data by using the thread ID and the block ID. So let's see how that happens. Okay, we can. So here we have an example of array summation. We want to add array A and array B and get the results stored into array C. It's important that the size of the arrays should be similar, so that's a given. So this is the sequence. So here we can see the simple C implementation of the array sum. So read it like this from here to, so it's a 2-column slide mini. So read it in this fashion. So we are going to include the standard IO library. We are going to define a parameter as the max size of the array. We are going to define those arrays into the stack. You can use a heap, and you can use allocation to allocate big chunks of memory and big chunks of arrays into the memory through the malloc function from C. But now we are just because it's 10 elements, we are going to initialize that into the stack. But it's not a good way to do, because if the size is big, you will get an overflow, hence the Stack Overflow name. Okay, so we are going to initialize that, initialize A and B, and then we, through a sequential execution manner, we create this for loop, which loops through different elements, adds them, and then stores the resulting element into C. So yeah, that's simple, I can say. But now let's look at the parallel example. Okay, so we abstract away that array summation into the kernel function. So we use this identifier for our compiler to know that this is a kernel function, this is a GPU code. We do the array summation, we pass in our variables by reference, so hence the asterisk sign, and then we are going to add them. So if you remember, you don't have to remember, but if you look here, the loop that we did within the C code, within the sequential conventional implementation, we had this I that that loads these pairwise elements of A and B and adds them together. But if we want to do that in the GPU, we are going to do the addition of each pair from A and B by a single thread. So I'm going to get the thread ID, meaning that the X here identifies the first ID of the thread identifier, the first dimension. So if it is thread 0 running this code, it loads A0, B0 and adds it to C0. If it's thread 2 running its code, it's going to be A2, B2. You can see that we are kind of parallelizing that for loop, that which would run sequentially into parallel execution by multiple threads. So these threads are going to run parallel together. Here, you can see that we are defining the size of the block and the grid. We are going to use dim3, which this is a struct. So we create 10 threads in a one-dimensional manner. To say that it's one-dimensional, we have to set the other dimensions to 1. So 10, 1, 1, and we are going to only create one block. So one block of 10 threads are going to run this code. So simple. We pass that to the function call and kernel invocation, it happens. So now one limitation is that you cannot go more than 512 threads within a single block. But what happens if we want to add two arrays of more than 512 elements? We have to organize our threads into more blocks. So what if we want to add an array that has 2048 elements? We are going to create 4 blocks of 512 number of threads. So that's simple. Now this is going to talk about the block ID, the grid dimension, and the block dimension. We are going to use these different variables. So these are given variables. We are not going to define them. So these get their values from the kernel and from the compiler at the runtime. So we don't have to set any values. That thread ID variable that you saw before, it gets initialized and it gets its value in the runtime and on the fly. So let's look at a neat way and a neat representation of what would be the different initialized values for the thread ID X, block ID X. So the thread ID, the block ID, and the block beam for these different threads within these different blocks. So for this thread, it is thread 0, so its thread ID would be 0. It belongs to block 0, so its block ID would be 0. And the block dimension, the number of threads within each block, would be 4. So it's not going to be a real surprise to you, but the block dimension for each thread would stay the same because each block has 4 threads. So in the case of these, for example, thread, the block dimension is going to be the same. It is the first thread within this block, so its thread ID would be 0, and its block ID would be 1. And that's how we can map it to data. As you see, if you're going to use the thread ID alone, this thread and this thread have the same address. But if we use the block ID times block dim, so 1 times 4, because we know there are 4 threads, and we add it to the thread ID, globally, this is the 4th thread in the grid. So that's how we map it. That's how we map these different values to the global address of each thread running within the grid. So as another example, this thread. So the block dimension is 4, no surprise. The block ID is 2, is the 3rd block within the grid. So these are from 0, like NumPy variables, NumPy indices. They start from 0. So this is 0 rather than 1. This is block 0 rather than block 1. This is the 4th thread. So its thread ID is 3. And this is the 3rd block. So its block ID is 2. So let's see another example. In this kernel, we have value A. Each thread is running this single code. The single instruction is that the thread is going to run, initialize the value of A. So this is the grid size and the block size. And initialize the value of A to your thread ID. Because each thread is going to see its own thread ID, A0 would be 0, A1 would be 1, A2 would be 2, so that's how we have it after execution. But if it was block dim, what do you think? Because we have 4 threads in each block dim would be 4, and it would be always initialized to 4 for each element of A. So now let's see the same thing, but using 2 blocks and the global address of each thread rather than its local address. To get the global thread ID or GT or the grid based thread ID or the thread ID within the grid, what we do is that we do this. So as we mentioned, this is the second thread of the second block. So we have 4 threads in the first block. So it would be 1. So block ID is 1. 1 times 4, 4 times the second thread. It would be the 6th global thread. Okay, so what we do is that when we add it, it maps to the same data rather than mapping to if we use TID or the thread ID alone, this thread would have mapped to A0 rather than A4. Okay, it maps to A4, it updates its value as its GTID as 4. So if you want to update it as the block ID, because each of these threads have the same block ID, these 4 threads are belonging to the block 0, so their block ID would be 0. You can see these are initialized to 0. These belong to block 1, so their block ID would be 1, so they are initialized to 1. So that's simple. So this was a way for you to see what are these different values, how are they initialized, but I know it was just too fast for the first time to capture it, and there's no worries. You can always come back to the presentation or look into tutorials to find out how this mapping goes. Because block ID, block dim, it might be confusing, the names might be confusing, but don't worry. It's only a way to get the global address of each thread within the grid to be mapped to the data. Okay, so in the previous case, as we mentioned, we had 10 elements. And having 10 elements and being limited to only 512 threads per each block, we need to go to more than one block if we don't want to use a for loop, essentially, because we don't want to use a for loop. We don't want it to be sequential. We don't want to run our code in a sequential fashion. If we want to handle all of those elements additions with a single thread, what we have to do is that we have to go more than one block. We have to have 4 blocks of 512 threads. Or here, we have 4 blocks of 2 threads, which is crazy. But yeah, oh, sorry. We have 2 blocks. So in the block dimension, this is a block dimension shows the number of threads within each block. As we have, in the case of some GPUs, we can go to more than 512 threads per block. It is maxed at 1024 threads. Here, the case is 1024 threads. So we have the data. We want 2 blocks of 1024 threads within each of those blocks. So we divide up the number of data by the blocks that we have. So it would be 1024 for the block dimension, and it would be 2 for the block for the grid dimension, meaning that again we have 2 blocks, each having 1024. So it's dictated by the hardware and the GPU that you're using. In case of the new architectures, you can use evidently more than 512 threads. And then when this segment of code is passed to the GPU to execute, these variables are initialized in the runtime, and each thread can get its global address, and then it's going to load and access the data A and B through its global access, and then update C. So simple. Yeah. So I must go over the memory access and the memory architecture within the CUDA. So it is a bit convoluted, I agree, and I'm not going to be talking about it in more depth than is required for this presentation. So for you to know, and as is required for you to know, each GPU So essentially it comes as a package, which has its own global memory, okay? So each GPU comes with a memory. When you go out and want to buy a GPU, if you want to buy a gaming GPU, the GPUs come with 16 DDR5 memory, 16 gigabytes of DDR5, 32 gigabytes. Nowadays they go up to 80 gigabytes, but it's limited to that. And when you buy the GPU, you want a GPU with more global memory size. So your host essentially has its own GPU, its own memory. So when you buy a laptop, you buy a 16 gigabyte of laptop. When you spec out your servers, you get 1 terabyte memory. You can get more than that as well. But that's the CPU and host memory, and each GPU has its own memory. The GPU memory is the global memory. As I mentioned, the threads and the block and the threads within a block have different access patterns to different memories. Each thread has access to its own registers. The threads have access to the local memory. The local memory is where the dynamic arrays and the arrays and also all sort of stack variables go to be stored. The shared memory is, as you can see, the shared memory is housed within a block. It's not housed, but in the execution, each block can have access to the shared memory. So threads can talk to each other through the shared memory. As you can see, threads can read and write their own registers, so they cannot have access to each other's registers within a block. But within a block, if you want to have inter-thread communication, you can do that through the shared memory. And then we have access to the global memory. We have access to the constant memory. The constant memory can be cached, might be faster. The local memory is also cached. So there are different types of cache memories. But essentially, what you as a programmer see is you can initialize variables on the GPU's global memory through the CUDA malloc, and you can transfer files between it by using the CUDA memcpy. You have the destination variable, the source variable, which is mostly a variable on the host or the CPU memory, or on the other devices. You can have data copy from one GPU to another GPU. You can see that here. And then the type of copy that you want to do. You want to copy the data from the host to device, or in reverse, you want to copy it from the device to host, from device to device, or is it a data copy from host to host? And then always remember to free up your data memory allocated on the GPU. So it might be okay for me to show the code. Okay. So let me log into this. A simple example of the program that we talked about. Let me zoom in. Okay.
Oh, we can't see your screen.
You cannot see my screen?
We just see the presentation.
Oh, okay. So I have to stop sharing and then start sharing again, because we don't have time, much more time about it. And I think those that have questions can stay longer if you have questions. Okay, so let me see. Can you see the terminal now?
Yeah, we can see it.
Okay. So let me see where I am. Okay. Okay. So this is an example of the vector summation code, the vector addition. So we have a vector summation. As you see, we are getting the global address of each thread, because we are defining these vector elements to have 24 million elements, and each vector would be having 24 elements within it. As you see, we are defining only 128 threads per block. So we are going to be using more threads and more blocks, sorry. So we are going to divide our data based on the number of threads that we have, and then run this. As you see, I'm not using that dim3 struct to run the to define the size of the block and the grid, and this is completely fine and better for programming, I guess. But this way, you can simply just say the number of threads and the number of blocks. That's simple. Okay, so let me start from the main. So with any C program, you should have a main, you should have a point of entry to your program. The compiler should know where to start. It starts here. So we want arrays of 24 million. We have to initialize them on the heap rather than the stack. And as I mentioned, these are the CPU variables. As I mentioned, I'm going to use malloc and the size. For the size, I have to define the size of int. So size of int in some cases is 4 bytes, 32 bits, and then times the number of elements. So I'm going to add 2 integer arrays together. If it was float, this should have been float, like float and the size of float, but must not do, okay. Next, I'm going to define the device variables and to allocate the device variables on the GPU. So device are the GPU. The GPU variables on the global memory of the GPU, I'm going to use the CUDA malloc with the same size. So these are things that I want to time the execution, so don't matter. I'm going to use the CUDA memcpy to copy A. So I'm now initializing A and B, which are variables on the host. And then I'm going to copy A to dev A and B to bdev from the CUDA memcpy. So from the host memory, from the CPU memory to the GPU memory. And that's going to happen here. That's simple. The direction is from host to device. And curiously, after we are done with our execution, the direction is put from device to host when we want to get the cdev results to be stored in C. So these are for timing. I define an event to time my execution. So I'm now going to invoke my kernel. These are the configuration for the organization of the threads and the blocks. I pass the device arrays, so adev, bdev, cdev, and these are timing, and this gets the latest error, so it runs without an error. So, and after all, I free the heap and the GPU memory as well. So, okay, so let me execute. To compile the code, I'm going to use NVCC. This is the compiler that you find when you install CUDA toolkit on your machine. Okay, I compiled it. There are different ways and different things that I can do to the compiler to give out more information, like I can get the PTX, but yeah. So you see, I timed it for 24 million array summation. The time is this much seconds. I don't know how much is it, like 0.3 seconds, 0.4 seconds. And there was no errors in the code. And yeah, that's it. So it's that simple. I can maybe see my GPU. You see I have 2 GPUs, 2 Tesla V100. These are good GPUs. So yeah, that's it. And I'm using CUDA version 11.3. So thank you, everyone. I hope that I didn't turn your mind into jelly by talking so much. So let me, yeah, that's it. So who has questions? Shoot for questions. Okay.
Excellent. Not seeing any in the chat right now, or anyone kind of chiming in. I think there's a lot to digest there, so I'm sure everyone's knows they can get a hold of you on the Discord channel anytime between now and the end of the sprint. So, Omid, thank you so much for the presentation today.
Thank you.
Excellent. And yeah, so we'll have more information about the project Swap Night. Other than that, we'll see you all on the Discord channel.